Um, Hello everyone. Today I'm going to present you the distributed computing for privacy-preserving data analysis. Here's an overview of today's presentation. Biomedical science is moving towards to the data-driven approaches. EHR data is increasingly being used in biomedical research. For example, the P-scanner project is integrating over 21 million patient data in biomedical research, and the GWAS study also requires a large number of samples to get robust results, such as the Kawasaki disease described in the previous presentation. Moreover, with the significant cost reduction, the whole genome sequencing data is now under $1,000, and next generation sequencing data is becoming very promising in biomedical research. So data sharing will play a very important role in the biomedical studies. For example, in the GWAS study of Kawasaki disease, a robust detection of a novel oocyte that is highly likely to be associated with the Kawasaki disease may require thousands of samples across institutions in different countries. But this requires gathering individual level data from multiple sites, but this is against the institutional privacy policy. So one common question is to share or not to share. One may restrict any data access to achieve the best data protection, but it also results in zero data usability. In contrast, someone may make data open accessible, which maximizes the data usability, but without provide any data protection. It turns out we need to develop some new method to achieve both high data usability and strong data protection. So in ADASH, we adopt the following three data sharing models as elaborated by Dr. Ono Machado in the previous presentation. So we have data archives models, share the data access, and distributed computing. In this presentation, I will focus on the distributed computing model, and where multiple institutions can collaborate with each other without sharing patient-level data and build a global model. And at the end of this presentation, I will introduce the shared data access model, which will link to Dr. Zhang's presentation after me. And let me introduce a typical distributed data analysis framework for parametric model that are generalized and linear. Assume there are two institutions and each has a private data set that they do not want to share, but they have motivation to collaborate with each other and conduct some data analysis to build a global model. So first, each site calculates some intermediate statistic locally. Then they send those statistics to a global server. And the global server calculates a set of global parameters. And the global parameters are sent back to each local data site to enable the calculation or update the intermediate statistic for a second iteration. So follow the same procedure, and we repeat n times until the global parameter converges. We can finally build a global model without the need to share the patient-level data. Based on this idea, we develop a great logistic regression model. It's compute a global logistic regression model without access local data from participating institution. The actual computation requires some derivation of log likelihood functions and its first and second derivative to be used in the Newton-Raphson algorithm. I will skip those details, but the audience can check our Gemini publication for more details. Moreover, we also investigate the Explorer framework, which is a Bayesian version of grid logistic regression. In contrast to the GROR, Explorer enables online learning and asynchronous communication between participating institutes. In the distributed computing framework, audience can also check our JBI publication for more details. Besides, we also turned the theoretical model into a practical tool, which offers distributed logistic regression building as a web service. We developed a Java applet and JavaScript service that treats individual browser as a virtual machine to conduct local communication and local computation and communicate with the central node through a secure channel. The servers can be launched in a user browser within minutes among collaborators to build a global model. Besides, we also develop a web disco framework, which stands for a web-based distributed Cox regression model as a counterpart of the WebGL. Web disco is similar to WebGL. We decompose the partial likelihood function and its first and second directive to enable the distributed computing for Cox regression model learning. In the next step, we are extending and scaling up our web-based distributed computing framework to handle large data sets in the Java study by leveraging the Linux-based virtual machine in a IDash cloud environment and designing new distributed algorithm for Java study. For example, we can get distributed allele frequency across multiple different institutes through a secure multi-party computing protocol. To enable the ready-to-run analysis, we are creating pre-built virtual machines in IDash cloud environment and the shared environment. And testing the automatic provisioning and configuration scripts for secure multi-party computing among virtual machines. We will launch those in our collaborating site in Atlanta, Singapore, and London next year for the Java study in Kawasaki disease. After downloading the pre-built virtual machines, each site only needs to configure its local network, such as IP address, and attach the local data to the virtual machine. Then it can consent to start the secure computing without sharing patient-level data. Here, the IDash at UCSD will host the global server to synthesize the global model. Now I will briefly introduce the shared data access model in this slide by using an example. Suppose an authorized researcher wants to query the number of females with heart disease in a restricted data set which is hosted in a secure cloud. Given this request, the cloud can conduct the calculation on behalf of the researcher on the restricted data set. Then a count of 12 as a result can be sent back to the researcher. Here, the researcher cannot access the raw data, and all the computation is finished within the secure cloud, and only the approved result can be shared. We propose a witness web service to implement the shared data access model. Here, witness stands for a web interface for interactive survival study. This is a collaborative project with the Strong Heart Study Coordinating Center hosted at University of Oklahoma Health Science Center. Dr. Zhang will discuss more detail about this use case in the next presentation. The front-end interface uses the standard web technology, where authorized user can easily conduct approved analysis, such as the survival studies in using Cox model in a browser. The backend service are implemented in a virtual machine and hosted in a secure cloud, where all the data and the data analysis tasks are performed in the secure virtual machine, and only approved result will be released to the authorized user. To achieve this goal, we also develop a fine-grained access control interface where we can add, modify, remove user and user groups. We also develop feature control and the data control modules. Under the feature control modules, we can add and remove supported analysis features for given user groups. And moreover, we can also restrict the accessibility of the data set for a given user. More precisely, we can control which variable and in which region this variable can be accessible for the given user. And here's a conclusion. And we would like to thank the funding agency and all the members in our teams. Thank you.
Thank you.